Hello everyone, welcome back to this channel. In today's video, we are going to continue with discussion on successive differentiation, which we started in the previous video, and learn a very important theorem called Leibnitz Theorem, which helps us to find out the nth order derivative of a product of two functions. Suppose u and v are given to be two functions of x which possess nth order derivatives, and we are interested in finding the nth order derivative of the product of u and v. Then this theorem, Leibniz theorem, helps us to find out the nth order derivative of this product through this formula, which looks like a binomial expansion formula. What you have to do is, the product's nth derivative basically follows a pattern which is given as you take the nth order derivative of the first function. So you'll have to decide one of them as first and one of them as second, and that decision will depend on your desire, what you want to prove. Accordingly, you will be choosing your u and v. That we'll learn in the applications. But once you decide your first and second function, the pattern is like this, that you take the nth order derivative of the first function, retaining the second function as it is as the first term. Then nc1, I hope everybody knows the binomial coefficient nc1. It's given by n factorial upon 1 factorial into n minus 1 factorial, and that's effectively equal to n, because ncr, all of us know, is n factorial upon r factorial into n minus r factorial. So nc1 is nothing but n. nc2 will be n factorial upon 2 factorial into n minus 2 factorial, which effectively becomes n into n minus 1 upon 2. Like that. So the pattern which is given by the Leibniz theorem for the nth order derivative is that you take the nth order derivative of the first function, retaining the second function as it is, plus nc1. In the second term, you will reduce the order of the derivative of the first function by 1 and increase the order of the second function by 1, so that the total order remains n in every step. So you can see nc1, un minus 1, v1, nc2. Now you'll reduce the order of un minus 1 further by 1, so that gives you un minus 2, and increase the order of v by 1, so v1 becomes v2, and so on. You will keep on continuing like this till you reach the last level, which is ncn u as it is into the nth order derivative of v. So that is what the theorem tells you, and it is easy to prove this theorem using mathematical induction, but we are skipping the proof right now and focusing on applications. Now let's understand this once again. If you are given a product of u and v and you are interested in nth order derivative, then you start like the nth order derivative of the first function into the second function as it is, plus nc1, keep reducing the order of the first function by 1 and increasing the order of the second function by 1 at every step unless the last level is reached, which is u as it is, 0th order derivative of u, which is u as it is, and starting with v, you will reach the nth order derivative of v, and that's the end of the story. So this is the formula which is given by Leibniz theorem, very easy to prove using mathematical induction. Let's start with the applications, which are extremely important and give you certain important recurrence relations. A typical application of this theorem looks like this. You will be given some function y and you will be expected to prove some relation between yn plus 2, yn plus 1, yn, or something similar to this. Now, if y is e to power tan inverse x, I am interested in something which is involving yn plus 2. So that means I need to do the nth order derivative of y2, because n plus 2th order of y will be obtained if I differentiate y2 n times. So the nth order derivative of y2 is nothing but yn plus 2. So what is expected to be proved tells you the level at which you have to take the nth order derivative. So this is an indication, clear-cut indication. This term yn plus 2 is clearly indicating that you will have to do y2 yourself ab initio. You will have to reach till the stage of y2 yourself and then apply Leibniz theorem to get yn plus 2 into picture. So you are interested in the nth order derivative of y2 according to the desired equation. So let's do that. Since y is given to be e tan inverse x, so what will be y1? E to power tan inverse x upon 1 plus x square. So simplifying that, this is the relationship that you get between y1 and y. But here you do not have to apply the nth order derivative, because here if you apply nth order derivative, then you are going to get yn plus 1 only, because the nth order derivative of y1 will be yn plus 1. But we are seeking something involving yn plus 2. So we will have to differentiate again with respect to x to obtain a relationship which involves y2. And once y2 comes into picture, you will apply Leibniz theorem. So this is how you decide that at what level you will be applying Leibniz theorem, because Leibniz theorem is going to give you the nth order derivative of something, right? And if the question expects you to land into yn plus 2, that means you're looking for nth order derivative of y2. So that means still y2 you'll have to move ab initio after differentiating the given function twice and obtaining a relationship between y2, y1 and y. Now once you obtain a relationship between y2, y1 and y, you will apply Leibniz theorem on both the sides. Now why is Leibniz theorem coming into action? See, y1's nth order derivative is nothing but yn plus 1. So the right hand side is just a single function. But on the left hand side you have two products appearing. There is a product 1 plus x squared times y2, and there is a product y1 times 2x. Both of them are functions of x. And we know that dealing with nth order derivatives of functions of x is something which is given to us by Leibniz theorem. The product of two functions, nth order derivative of the product of two functions. So on the left side you see that there is a product of two functions 1 plus x squared and y2, and there's a product of two functions y1 and 2x. So here when you apply the Leibniz theorem, you take the nth order derivative. So this is not an application. The right hand side is straight y1's nth order derivative, which is yn plus 1. So I get this term straight away. No use of Leibniz theorem on the right hand side. But on the left hand side you do have two products appearing, so you will apply Leibniz theorem to each one of them. So let's look at the application of Leibniz theorem to this 1 plus x square into y2. Now pay attention here. You have 1 plus x square as one function and y2 as the second function on which you are intending to apply nth order derivative. So the theorem says that the nth order derivative of this product is going to be first function into the nth order derivative of the second function. And at every step you are going to increase the order of the first function and take binomial coefficients together with that. Now what will happen is you take 1 plus x square here, and the nth order derivative of y2 will be yn plus 2. And then you will have nc1. The first order derivative of y1 plus x square is 2x, and a decreased order of yn plus 2, which is yn plus 1. nc2, another order. You will have to move to the next level of the derivative of 2x, that's 2, and then reduced level of this. Now the next term nc3, you will have the derivative of 2 this time, which is 0, and a reduced derivative of this. So you can see that the subsequent terms are going to be 0, and that is what makes you decide what your first function and what your second function should be. You will always take the first function as that function whose derivatives are going to vanish after certain number of terms. So 1 plus x square as it is into the nth derivative of y2, which is yn plus 2, plus nc1. You'll reduce the order of yn plus 2 by 1, that's yn plus 1, and increase the order of this by 1, which is 2x. So first order derivative of 1 plus x square is 2x. The second term is nc2. Now further decrease this by 1 and increase its order by 1. So you get yn here and 2 here, and the process stops here. You have applied Leibniz theorem to obtain the nth order derivative of 1 plus x square into y2 successfully, and you do not have to consider more terms because rest of the terms are going to be 0 according to the choice that you have made for u and v. Now similar choice made here for the product y1 into 2x, it is obvious that you will do what? You will say 2, you will apply Leibniz theorem to y1 into 2x. So you'll treat 2x as the first function and y1 as the second function. So first function into the nth order derivative of y1 is yn plus 1. nc1, increase this order. You have to take the first order derivative of 2x, that's 2, and decrease the order by 1 here, so that's yn, and the next terms are all going to be 0 because the next order derivative of 2 is going to be 0. So this is what you get as the nth order derivative of y1 into 2x, and right hand side is nth order derivative of y1. So when you simplify all of this, you get the desired conclusion. You put together the terms involving yn plus 2, you take together the terms involving yn plus 1, you take together the terms involving yn, you get the desired conclusion. So this is a typical peculiar problem based on Leibniz theorem. Leibniz theorem helps you to find out the nth order derivatives of products of functions, and whenever you see a recurrence relation kind of a thing, here yn plus 2 is being obtained in terms of yn plus 1 and yn, which means every second derivative is coming in terms of the first y0 and y1. So y2 is in terms of y0 and y1, y3 is in terms of y1 and y2, but y2 was in terms of y0 and y1. So effectively you are obtaining all the derivatives in terms of the first two, and that's what is known as recurrence relation, and that's the most important application of Leibniz theorem. So Leibniz theorem is basically a theorem which helps us to find out the nth order derivatives of products of functions, and we apply them to obtain such recurrence relations. So this is one question which you can try on your own on similar lines. Earlier in this question we had e to power tan inverse x, and this is just y equal to tan inverse x. So you'll do y1 will be 1 upon 1 plus x square, and since you are not in a position to apply Leibniz theorem at y1, because that's going to give you something involving yn plus 1 only, but the desired result involves yn plus 2, so that means you'll have to go up till y2 ab initio. So the relationship 1 plus x square into y1 is 1 needs to be differentiated once more before you apply Leibniz theorem. So you differentiate this again, 1 plus x square as it is into y2 plus y1 into 2x is 0. Now you should apply Leibniz theorem to both the terms and obtain this relationship. So that's how Leibniz theorem needs to be understood, because you cannot see, there's nothing wrong when you apply Leibniz theorem here. It's very much applicable, but it's not giving you the desired conclusion. The desired conclusion is involving yn plus 2. So that means you are seeking nth order derivative of y2. So reach till y2 ab initio and then apply Leibniz theorem that to obtain the desired conclusion. So it will very much depend on what you need to prove. That decides the level at which you apply the Leibniz theorem. So let's look at one more question. So you must try this question on your own, and it's an easy one, very similar to the previous question. Now if y sine inverse x, let's look at a similar question. Again, a relationship involving yn plus 1, yn and yn plus 2. So that means you'll have to go to y2 yourself and then apply Leibniz theorem on both the sides. So let's do that. Y is this, so y1 is this. So this is the relationship that you get between y1 and x. But here we are not in a position to apply because the desired result is involving yn plus 2. So let's move till y2 on our own. So one more differentiation gives us this relationship between 1 minus x square y2 minus x y1 is 0. Now if you apply Leibniz theorem, because this is a product of two functions, this is again a product of two functions, right side is 0, so take nth order derivative on both the sides. On the left side, since it's a product, so its nth order derivative will be obtained using Leibniz theorem, and obviously the choice will be that this is u, this is v. U as it is, nth order derivative of v, that means nth order derivative of y2, which is yn plus 2. And then you keep on increasing, attaching binomial coefficients. This is going to vanish all the derivatives of minus 2. After this term, there will be all zeros, so you don't have to write them. And similarly, you can apply Leibniz theorem here and combine the terms involving yn plus 2 together, yn plus 1 together, yn together to obtain the desired relationship. So that's how typical questions on Leibniz theorem look like. So this is one more practice question for you. Please take a screenshot and try proving it on your own. If you get stuck in any of these questions, you can please write your confusion or whatever step you are stuck at in the comments. We would love to help you and help you to come out of that problem and reach the final conclusion. But these are really easy problems once you understand the crux. The crux is that Leibniz theorem applies to products for obtaining nth order derivatives of products. So products have to come into picture. So you'll have to bring in products yourself through one or two differentiations according to what is desired in the question. So this is apparently yn plus 2 according to me, because there's a yn plus 1 here and there's a yn here. So this should be yn plus 2, but you can still check on your own. you will reach till y2 on your own and then apply Leibniz theorem to check that the conclusion is very much valid. Now look at this problem, another typical problem where you are again seeking a relationship between yn plus 2, yn plus 1 and yn, but the problem is that y is not an explicit function. In the previous problems, y was given explicitly, so you could do very easy differentiation on both the sides. Y was an explicit function, but here y is given implicitly. And if you recall in your classes, earlier classes, you have already learned how to solve for y. Such equations can be solved for y through a very basic assumption that suppose we substitute t as y to power 1 by m, then this is actually a quadratic in y to power 1 by m. This is t, this is 1 by t, this is 2x. So that means you can treat it as a quadratic in t to solve for t, but t has been the name given by us to y to power 1 by m. So basically you are able to get your y explicitly like this if you just use your elementary knowledge of quadratic equations. Now once you have y, the conclusion is about yn plus 2. So we'll do a similar thing here. We'll do y1, obtain a relation. We'll do one more differentiation, obtain a relationship, and so that y2 pops into picture. Once y2 comes into picture, everything is set for you to apply Leibniz theorem. Once you apply Leibniz theorem, you are able to get the desired conclusion very easily, because the choice of u and v is understood by us, that we take the first function to be that function whose derivatives are going to vanish after a certain number of terms, because that simplifies our formula which is given by Leibniz theorem. So let's try, this is another problem, unsolved problem for you to try on your own. You can take a screenshot and please try it out. Let's look at another solved problem which I have included in this video. You can see y is given to be a cos log x plus b sin log x, and you're expected to again obtain a relationship between yn plus 2, yn plus 1 and yn. A very similar question, a very similar exercise. You can check the calculations. y1 will be this. Another step of differentiation is required because again we are seeking yn plus 2. So one more differentiation gives you a relationship between y2, y1 and y. And once you have a relationship between y2, y1 and y, you are in a position to take the nth order derivatives on both the sides, because once y2 comes into picture, its nth order derivative is going to be y's n plus 2th order derivative, and this is what we want to bring into picture. And why is Leibniz theorem coming into action? Because the relationship is involving products, and for products, nth order derivatives are obtained using Leibniz theorem. So this very elementary, calculation gives you, once you take together the terms involving yn plus 1, the terms involving yn plus 2 and yn, you get the desired conclusion. A similar question has been included in this video just to make you practice a little more on this. And here it will be more convenient. It's entirely up to you. If you do this like maybe a y sine inverse x upon root 1 minus x square, so it will be better to take y square into 1 minus x square is sine inverse x square. You can start differentiating from here. That will be a better way of handling it. But if you don't like it this way, you can do it ab initio and just see you are seeking something which is only involving derivatives up to yn plus 1. So you'll just go up till the stage of y1 and apply Leibniz theorem. You don't have to find y2 in this case, because the question does not expect you to get something involving yn plus 2. So you'll straight away, once you obtain y1, you'll straight away apply Leibniz theorem to get the desired conclusion. So please practice this question. If you get stuck anywhere, please put your doubt in the comment section. We would love to help you with that solution. Now look at this one again. A similar question but a little technical. Again, y needs to be separated because we like y being on one side, so that differentiation is easy. A very easy manipulation of the given equation leads to y being this, and differentiating you get a relationship between y1 as x into y1 is minus nb sine n log x by n. It's very easy to see that we have used the property of log here. Log x by n to power n comes out, that's the property of log, and then you take this cos here and then b is attached. Okay, yeah, so this is not the right stage to apply Leibniz theorem, because what are we expecting? We are expecting yn plus 2 to come into picture. So let's bring in y2 first. So differentiating once again, you get this relationship between y2, y1 and y, and once you have a relationship, you are all set to apply Leibniz theorem looking at the desired conclusion. You do get the conclusion once you collect the terms involving yn plus 2, yn plus 1 and yn. So a similar question has been given for you to try here, but I've included the solution here because there was a tail attached to the question which expects you to find the nth order derivative of this function at 0 also. So such questions which have this tail attached amount to a little bit of more work towards the end of the question. So let's quickly have a look at the solution. Y is given to be sine inverse x square. An easy differentiation on both the sides gives you this relationship, but since yn plus 2 is expected to be coming in the final question, so one more differentiation has been done, and then Leibniz theorem has been applied to get the conclusion. So the conclusion was easy. It was a routine task which we have been doing in the previous questions, but this tail in which you are expected to calculate yn at 0 is something that one needs to pay attention to, because this is the first question of this type in this video. Now see, this relationship is valid for all x. This is what you are obtained for the function y equal to sine inverse x square. We have obtained this relationship no matter what x is. So in particular at x equal to 0 also this relationship should be valid. Why are we putting 0? Because we are being asked to find the derivative at 0. So let's include that point in this relationship to simplify the relation that we have got. In particular at x equal to 0, when you put x as 0, this becomes yn plus 2. This vanishes because it's a product which is involving 0. So this is 0. So this is what the relationship simplifies to once you put x equal to 0 from what you have got here. Because you are seeking yn at 0, that's the reason of putting 0 in your recurrence relationship. At 0, we look at the simplified relationship when we substitute x equal to 0 and try to see how derivatives behave at 0. Now this means that every n plus 2th derivative has a connection with nth. So second derivative will have a connection with 0th derivative. Third derivative will have a connection with first derivative. Fifth derivative will have a connection with third derivative, but third derivative has a connection with first derivative, and so on. This will have a connection with fourth derivative, sixth derivative. So this is how pattern is being formed here. So that means all derivatives are going to be coming in terms of a first few derivatives only. So let's examine y at 0. Since y is sine inverse x square, so what is y at 0? It's 0. What is y1 at 0? This is true for every n greater than or equal to 1. So what is y1 at 0? When you look at your y1, what was y1? Look at y1. When you put y1, sine inverse 0. So y1 is also 0. Now look at y2. So from here, if you see, what is y2? y2 is 2 plus x y1 upon 1 minus x square. So at x equal to 0, what will happen? At x equal to 0, y1 is 0. We have just now seen. So this term is 0. This is gone. So y2 is 2. So we have got some derivatives, initial derivatives through the values that we have substituted. And now look at the relationship that you have got towards the end. You can see that since y1 is 0 and every odd derivative is dependent on y1, so all odd derivatives of this yn is 0. That means yn is 0 for every odd n, because every odd order derivative is ultimately dependent on y1, but y1 is 0. So all odd order derivatives are 0. So let's take n to be even now. Now this is true for n greater than or equal to 1. So let's take the first even natural number. First even natural number is n equal to 2. So y4, when you substitute n equal to 2 here, what do you get? y4 is 2 square into y2, but y2 is 2. So it's 2 square into 2. What will be y6 now? For n equal to 4, what do you get? yn is 4. So y6 is 4 square into y4, but y4 was 2 square into 2. So this is what it becomes. Similarly, you keep on substituting the values, you keep on getting a pattern. You can see that at the nth level, if n is even, at the nth level it's going to be 2, 2 square, 4 square, so on till at 8 you were getting 6. So at n you are going to get n minus 2 square. So this is how you have to analyze a little bit of the recurrence relationship at the point x equal to 0 to derive your nth order derivative at 0. And if you accumulate the information that you have got about yn, in the previous steps, what did you get? You get yn is 0 if n is odd. For every odd it's 0, but if n is even, it's not 0. It's following a pattern which is given by this formula. So this is how you need to simplify, observe a pattern, and then ultimately write your yn at 0 in a form which is presentable towards the end. So let's look at a similar question. So I have intentionally included such questions in which there is a tail attached, yn0 tail attached to the question. Now this question is not seeking any recurrence relation, but since it's asking for yn0, it's good to derive a relationship on your own. So this question was not giving you the relationship. Still, Leibniz theorem has been applied to obtain the relationship like this. And once the relationship is obtained, this relationship is true for every x. Now we are interested in the point 0. So let's substitute x equal to 0 here to simplify the relationship and study the function for this simplified relationship. Let's study what the pattern is, how the derivatives are behaving. So at x equal to 0, yn plus 2 is n square minus m square times yn. M was a fixed constant given in the question. M is something known to us. N is something that is varying. N is a natural number. Now this again, every odd derivative depends on y1, every even derivative depends on y0, y2, etc. So let's calculate the first few derivatives on our own. Yx was given to be cos of m sine inverse x. So what is y1? yz. So let's look at y at 0 first. So that's y0 at 0, 0th order derivative of the function. Cos of 0 is 1, so y0 is 1. Now let's look at y1. y1 means the first order derivative of y. Let's see what is the value of y1 at 0. Since sine inverse 0 is 0, it's sine of 0, that's 0 again. So that means through this relationship you can see that every odd derivative is going to be dependent on y1, so every odd yn is 0. But for even n's, it's going to follow a similar pattern as we got in this previous question. So this is the pattern which will be followed if n is even, because y, you'll be keeping on giving on values to n. When n even case is being discussed, the first n that you will take is 4. Y4 will be obtained, n will be taken as 2, so it will give you y4 is 2 square minus m square into y2. But y2 had some value. You had y2 in terms of y0. y0 was 1. So this is y2. This should have been done earlier. So y2, when I put n equal to 0, what do I get? It's 0 square minus m square into y0. But y0 is 1. So it's only minus m square. So this y2 when substituted here makes y4 as 2 square minus m square into minus m square. So it's going to begin with minus m square and it's keeping on increasing at every level up to what level? If you are seeking nth, it's n minus 2th level up to which you are going. See, 4th, it's going up to 2. 2, it's going up to 0. So at nth, it's going to go up to n minus 2 square minus m square. So this is the answer to the question of finding yns at 0. So yns at 0 are given by, I should have written yn0 is 0 if n is odd, and it's given by this formula if n is even. So there are similar questions which have been included in this video for your practice. You can see earlier in the previous question we had a cos here. It's a very similar question, very similar pattern. So please try this question on your own. A similar question has been done earlier just to find the recurrence relation. It was there, but here you have a tail attached, yn0 tail attached. So please try these two questions also on your own. And if you get stuck anywhere, please put your doubt in the comment section. We would love to help you. The crux of the matter is that if you have a product of two functions appearing in any of the questions involving nth order derivative, then Leibniz theorem comes into action. Now Leibniz theorem comes into action on anything wherever the product is involved. You will have to look at what you desire to prove to decide your stage at which you will be applying the Leibniz theorem, because Leibniz gives you nth order. So if you are seeking n plus 2th order, then you will have to apply Leibniz at the y2 stage. If you are seeking n plus 1th order, you will have to apply Leibniz at the y1 stage. And if you are seeking nth order, you will straight away apply Leibniz theorem to the product of the two functions. It's going to come into action only when you see a product, not otherwise. That's all for this video. Thank you so much for watching.